So this one is exercise related to electromagnetic effects and the doubts related to this exercise. The first one is question 10, part B. So question 10, I'll solve both parts, 10A and B. This is question 9. So we have question 10. The northern lights are a colorful display which can be seen on the North Pole. They are created by interaction between the air molecules in the upper atmosphere and the charged particle from a solar wind, which captured by Earth's magnetic field. It's also produced by radio waves. The charges follow a circular path, emit electromagnetic radiation at a frequency of their circular. We have to show that the electron with a speed of 400 km per second will emit a radiation with a frequency of 200 kilohertz if it is moving perpendicular to the magnetic field with a magnetic flux density of 6.8 microtesla. So the idea which we will use, because we want to show its frequency. So moving in a circular path, when object rotate or move in a circular path, the speed is distance divided by time. But when object is moving in a circular path, speed is 2 pi r and time is t. But for one complete rotation or revolution, the time is known as a time period. So we can say V is equals to 2 pi r divided by t. And time period is actually reciprocal of the frequency. So we can say V is equals to 2 pi r into f. So if we need f, it will be equal to V divided by 2 pi r into f. So to get the frequency, what we need the speed and we need the radius of this circular path. As there is a magnetic field, the magnetic field will cause a deflection. So how we can work out the radius? The centripetal force will be equal to magnetic force. When object move in a circular path, the centripetal force will be equal to magnetic force. This centripetal force is given by a formula mv square over r. And magnetic force, when particles are moving perpendicular, it's qvb. So we will cancel with square of this. So we are left with mv over r is equals to qb. So we have the strength of a magnetic field. We have the charge of electron, which is 1.6 exponent minus 19. We have the speed as well, that is kilometer per second is given. So we convert into meter per second. And we have the mass of electron, which is 9.11 exponent minus 31 kg. So we can find the radius here. So we'll have the radius. So using this radius, like we got the radius here. As you can see, speed is already there with us. So we have the speed, we have the radius. So we just substitute V divided by 2 pi r, we'll get the frequency. Part B. As you can see, the cosmic rays particle which are entering the Earth magnetic field follows a spiral path through the atmosphere. In the region of a North Pole, the magnetic field is vertically downward, and the diagram shows the electron enter the section of this field. Explain why the electron follows a clockwise spiral path downward as seen from above. So this electron will have the two components. When it enters the magnetic field, one of the component of the velocity will be parallel to the magnetic field. Another one is perpendicular to the magnetic field. So it means the vertical component, which will be parallel to magnetic field, and horizontal component is perpendicular to magnetic field. As a result, what will happen? So as you can see, there are two components. One is a vertical component, another one is the horizontal component. Vertical component is parallel to the magnetic field, and horizontal component is perpendicular to the magnetic field. So the component which is perpendicular to the magnetic field, that will cause circular motion, and the component which is parallel to magnetic field, that will cause a displacement. So this will move, this electron will move in this manner, because two components of velocity are there at all the points. One is parallel to the magnetic field, another one is perpendicular to the magnetic field. Perpendicular causes circular rotation, circular motion, and the parallel to the magnetic field will not cause any change in the velocity, but still is there. That's why it will move downward. So how you will score the 3 marks? You will mention the force which is perpendicular to the path of the resultant circular motion, like there will be a centripetal force. So the horizontal component is perpendicular to the magnetic field. So there will be a centripetal force which causes a rotation in a, or it which causes a circular motion. Where the vertical component of the velocity which is parallel to the magnetic field, it will not experience any force, it will not cause any acceleration. That's why it will move downward. Like there will be all the positions, there will be a constant force acting downward. So when we draw the trajectory of this, so it will have a circular motion in a clockwise direction, and there is always a downward motion is there due to the vertical component. So vertical component parallel to magnetic field cause a downward motion. Horizontal component perpendicular to the magnetic field cause a circular motion. And circular motion, the force is always directed towards the center. So the next question, question 13. The photograph shows a demonstration of electric motor. This is electric motor which uses split, as you can see, these are the split rings are there, carbon brushes and the rectangular coil. When the current passes through it, it experiences the force and the coil rotates. Electrical energy changes to kinetic. The coil of a wire is mounted on an axle that it can rotate freely. The magnets are placed either side of the coil, and when there is a current in the coil rotates. The diagram represents the coil and the magnet viewed from the end and from above. Number of the turns are given. Length of AC of coil is given, and only side AC is given, and the magnetic flux density is also given. Coil rotate clockwise as seen from A and AB. Explain the direction of the current. So how we can identify whenever we want to find the force on the wire in the whenever we want to find force, we always use the Fleming's left hand rule, because Fleming's left hand rule is used to find the direction of the force on the wire placed in a magnetic field. So because like this side is experiencing, it's rotating clockwise, so this one is experiencing a force outward out of the paper, this side is experiencing force outward, and this side is experiencing a force inward. Or you can say this is, if you are looking from the end, this one is going up, this one is going down. So when you apply the Fleming's left hand rule, your index, we don't know the direction of the current. So if we apply the rule here, like we want the direction of the force to be outward. So example, if we consider the direction of the current is from A to C. So if the current is from A to C, so our index finger, the first finger should point, the index finger or the first finger point in the direction of current. The first finger should point in the direction of a magnetic field, which is from north to south. So magnetic field is from north to south, so index finger should point in towards the right hand side. That is the first finger. The second finger represents the direction of current. So index finger is pointing in the direction of a magnetic field, which is toward the right hand side. Second finger represents the direction of the current. So example, we don't know the current, but if we consider the current is from A to C. So if the current is from A to C, our index finger will point in the direction of the current, and that is according to this one, it should point upward. We are applying a rule here. So where your thumb will point, so first finger represent magnetic field, second represent direction of current. So where your thumb will point, your thumb will point into. But we don't want into, we want out. So if the current is not from A to C, the current should be from C to A. So by applying a Fleming's left hand rule, so current should be from C to A. When current is from C to A, the direction of a force, when we apply the Fleming's left hand rule, it will come outward. And we want the force to be outward, not into. So the force will be outward. So here the direction of a current is from C to A. Then calculate the maximum force on side AC when the current in the coil is 0.29 ampere. How we can find force on the wire which is placed in the magnetic field, and if it is perpendicular, so F is equals to BIL sine theta. But when it is perpendicular, it's F is equals to BIL, where B is the strength of a magnetic field, which is given in the question 0.074 Tesla. The current is, they mentioned it is 0.29, and the length of this section of this wire, as I mentioned, the length of side AB is how much? 48 centimeter, but it turned 32 times. So how much is the total length of section AC? So it will be 0.48 because 4. So that was equals to 4.8 centimeter. So we convert into meters. So 0.048 will be there, and multiply by 32 because total 32 times the wire has turned around. So when we multiply this, we'll get the force, which will come out about 0.033 Newton. So F is equals to BIL. In part C1, when the coil rotates, the average current in the coil is less than the current of a coil which, if it is held stationary. This is because of a production of a back EMF. Explain how the back EMF is produced. Basically, what happened, as we know, according to Faraday's law, that whenever there is a change in magnetic field, there is always a current. So first, like if we were having two magnets and we place a rectangular wire between the magnetic poles and we are passing a current through it. So when we are passing a current through this, the wire will experience the force one side in, one side out, and it start to rotate. But when the coil is rotating, there is also a change in the magnetic field. And this change in a magnetic field produce a current in opposite direction. That is known as the voltage is known as the back EMF, and the current is a induced current. So what happened? Due to rotation of the wire, there is a change in magnetic field, and that change in magnetic field produce a current. And that current it's always opposite to a direction of the initial current. Like if initially the current was from C to A, but due to the rotation of this coil, there will be another current, but that will be from A to C. And that current is due to the change in the magnetic field, which is also known as the induced current, or the voltage produced is known as induced voltage. So if the current which we were passing is 0.29 ampere, but the back EMF, due to back EMF, the current is example 0.11. So the total current which will flow out will be different. It will not be 0.29. It will be less than 0.29. But when it is stationary, there is no change in the magnetic field, so there is no current produced. Because when the coil is stationary, the magnetic field does not change. If the magnetic field does not change, there is no induced EMF. So the points here, when the coil rotating, explain how the back EMF is produced. So how this back EMF is produced, we will mention when the coil is rotating, there's a change in the magnetic flux linkage as a coil turn or rotate. And the wire in the coil cuts the magnetic field, you can also mention. And due to that, there is induced EMF. And according to Lenz's law, the induced EMF is always opposite to the direction of potential applied or a voltage applied, or always try to oppose the change. So the rotation of the wire produce the change in magnetic flux linkage, because there are more turns, so that's why magnetic flux linkage, which induce EMF, or you can say current. And according to Lenz's law, the EMF induced always oppose the change in magnetic field or the potential applied. The next part, a wire of length L is moving at a speed of v through a magnetic flux density B. As shown, the magnetic field is into the page, so that the EMF produced is given by E is equals to BLV. So how we can show that the EMF produced is equals to B is equals to EMF is equals to BLV. So we have the formula, because the change in the magnetic flux linkage is equals to EMF. Like EMF is equals to N phi, or rate of change in magnetic flux linkage. So you can also say delta phi by delta D. Now we want to prove that the induced EMF is equals to BLV. So the flux is given by B dot A. And what about the flux is given by formula B dot A? And what about A? Area which it cover, because this is the total length and it is moving this is. So area is length multiplied by width. So example, how much distance it has covered, like we have the formula speed is equals to distance over time. So this total distance covered, because we want the total area it covered, move. So if we need the distance will be equal to speed into time. So distance is speed multiplied by time. So I can say B, means the phi is equals to B. And what about area? Area is length multiplied by width. So this is length and width is D. So area is equals to L into D. And what about D? D is equals to, like this D is equals to speed into time. So speed here we can represent by V instead of S. So speed is, this will be V into T. Now the EMF is equals to change in rate of change in magnetic flux linkage. So it is N delta phi divided by delta T. So phi, change in magnetic flux linkage. N is the number of turns, because we have only one here. So N, the value of N is equals to 1. And what about delta phi? So delta phi will be equals to B, L, V, and T. And what about the time delta T? So that is equals to T. Like it starts from 0 and ending at T, so time is T. So T will cancel with T. So what we are left with? We are left with EMF is equals to BLV. So we start with a magnetic flux, and the magnetic flux linkage we relate by EMF. Then the third part, the coil of a motor rotate 9 rotation per second. Calculate the maximum EMF across the width of AB is given 2.4 centimeter. Yeah, question 13 I will discuss full. Question 13, 14, and then 16 and 17. So here they already, like we already have the formula they mentioned. The rotation per seconds are given. We want to find EMF. The width is also given. So we will use a formula. We have the EMF is equals to BLV. And what about V? Because it's rotating, so it's an angular velocity which is equals to 2 pi r divided by t. Or you can also, the angular omega, this one, omega is given because it's rotation, 9 rotations per second. So this is omega. So you can also use a formula V is equals to R omega to get this V. After getting a V, the width of AB is there 2.4, but we need the radius. Like, so it will be half of it. So here the width of AB. So width is given for AB, but we need a radius, so we'll take just half of it. So rotation of the coils. So we'll find angular speed V is equals to, we'll find the speed V is equals to 2 pi r divided by t, or we can also use V is equals to R omega. So 2 pi r divided by t, or the time period for revolution, you can work out the time period. This is like 9 revolution per second. So every second, it's making like time to complete one vibration. So it will be reciprocal, or time to complete one rotation. It will be reciprocal of omega. So any of the formula you can use to work out this V. For example, if we use V is equals to R omega, and omega is equals to 2 pi divided by t. So we can say it will be R, means because the value of the omega is equals to 2 pi divided by t. So we can say V is equals to R, in place of omega, it will be 2 pi and divided by t. T is a time period. And how we can work out the time period? Look, 9 revolutions or 9 rotations in 1 second. So time to complete one vibration, it will be, the time period will be 1 over 9. So if I substitute, and the width was given, as the width is 2.4 centimeter, with that is the width. We need the radius because it is moving around the axle. So that we'll take half of it. So it will be 1.2 centimeter. So 1.2 centimeter we convert into meters, 0.012 multiplied by 2 multiplied by 3.14 and divided by 1 over 9. This will give us the speed at which it is moving. Because the formula for EMF is equals to B, V and L, where L is the length, B is the strength of magnetic field, and V is the speed at which it is moving. So first we work out the speed. The length is already given to us. But don't forget to multiply its length. Like now, after getting the V, say the V is coming out as 0.62, 0.68. After getting V, the strength of a magnetic field is 0.074. The speed at which the coil is rotating, 0.68, multiply by length of the coil. Like we just take length of any ones, 0.048 as it was there. 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 Length of side AC, like this is the side which is swap around, move around. That's why we just take this side. So 0.048. And because there are 32 turns, it's a continuation of the question. So total 32 turns are there. So you'll multiply by 32. So 0.048 times 32. So when you multiply all of them, you will get the induced EMF, which is 0.077. In the fourth part, the current in the coil varies as the coil rotates because of back EMF is not constant. So just why the back EMF is not constant. So what is the reason? Because when the coil is rotating, the coil is like the angle of the wire or the velocity changes. Like when it is, some cases it is exactly perpendicular, some cases it's less than 90 degree. So the wire cuts the magnetic field in opposite direction at every half. So rate of change of magnetic flux also changes. Like as this coil is rotating, the angle of the coil to the magnetic field vary, or angle is changing. As a result, the rate of the change of flux will also. So when this coil is exactly like, as you can see, this is a coil. First, it is exactly parallel to magnetic field. Then this will be the new position. Then this will be the new position. Then this is the new position. So as a result, what will happen? The angle of the coil is continuously changing with the magnetic field. So as the angle of the coil is changing with the magnetic field, the magnetic flux, like the change in the magnetic flux linkage or magnetic flux linkage or rate of change of magnetic flux linkage will also change. That's why the induced EMF is not constant. So the points you will mention here, that why the the back EMF is not constant, because the angle of coil changes with magnetic field, or it is not constant. So the rate of change in magnetic flux linkage is not constant. That's why the induced EMF will be different, like induced back EMF will be different. The average current in the coil can be measured using with an ammeter. Suggest a method of measuring how the current vary over. Suggest a method for measuring how the current vary over a time. So when a current is continuously changing, it's difficult to measure the current with an ammeter, because what will happen, an ammeter continuously it will change. So analog ammeters are not useful. In that case, we'll use a data logger and then we'll connect to a current sensor in series. So we use a data logger because data logger interface with the computer will keep the data, like record, or you will have that current at different time interval. Otherwise, if analog ammeter is used, it will continuously change. You will not find it easy to measure. So use data logger and we'll connect current sensor, and current sensor should always be in series because the current is same in series. So this was question 13, part D. Then we have question 14. The current carrying wire is placed in a magnetic poles. U-shaped magnets are there. Determine the magnitude of the force on the wire due to the magnetic field. You may assume that the field is uniform. So we have the formula F is equals to BIL. Length of the wire in the magnetic field is shown. The magnetic flux density is given. The formula F is equals to BIL. And the wire is perpendicular to the magnetic field. So we don't use, if the wire is exactly perpendicular to the magnetic field, we use F is equals to BIL. But if the wire is not exactly perpendicular to the magnetic field, then we have to use the angle here, like BIL sine theta. So first we work out the angle with the magnetic field, like this is 3.2. The length of this wire in a magnetic, this is 6.9. So the magnetic field from north to south, so magnetic field will point from north to south. So what will be the angle between the magnetic field and the wire? So we can use like this is making a right angle triangle. So this is 6.9, this one is 3.2. If I need the angle between the wire and this part is a magnetic field and this is a wire, L and B. I need the angle between them, so I need theta here. So this making a right angle triangle. This one is a hypotenuse for us. This one is a base, and this one is a perpendicular. So we use cosine theta. Cos theta is base divided by hypotenuse. So first we'll find the angle using a cosine theta. We work out the angle as one of the value, like the base is 3.2 and hypotenuse is 6.9 and theta, cosine theta, and then theta will be cos inverse 3.2 divided by 6.9. So this will give us the value for theta. How much is this? Cos inverse 3.2 divided by 6.9. 62.4. So the angle is 62.4 degrees. So now we have the angle. So F is equals to BIL sine theta, where B is the strength of magnetic field 0.074 Tesla. A is a current, which is 0.82. L is the length of wire, which was in centimeter. So we have to convert into meter. So 0.069 and then sine and then 62.4. So when we multiply all these factors, we'll get the force, which is about 0.0037 Newton. That's a force which this wire will experience in a magnetic field. But if the wire was exactly perpendicular, then we don't have to use sine. Like the wire was placed like this. So it's exactly perpendicular. In that case, the sine 90 will be 1. So we don't have to use sine. We just F is equals to BIL. Explain the direction of the force on the wire. So for finding the direction of the force, the direction of the current is given to you. So you have to use the Fleming's left hand rule. Your index finger, your first finger should point in the direction of a magnetic field, so downward. Your second finger point in the direction of the current. When you this is the direction of the current. So your second finger should point in the direction of the current. So when you apply the rule, the Fleming's left hand rule, when you apply this, where your thumb is pointing into the page when you apply the left hand rule. So the answer here, the direction of the force on the wire, so that is into. And how we work out into the page and how we work out or how we calculate that, or how we find that, not calculate. So we find it by using Fleming's left hand rule. The left hand rule is used to find the direction of the force on the wire placed in a magnetic field.